Our little planet Earth contains many different elements that you can find in the periodic table. These include metals such as silver, brass, iron, copper, and aluminium. Though these elements are known as metals, but they differ from each other based on their mechanical properties, electric properties, magnetic properties, chemical properties, and thermal properties. The main emphasis of this section will be on the use of distinct thermal properties of different materials. Bimetallic strip is one such device which relies on the varying thermal expansion of different metals. This means that it is based upon how different metals behave differently. In other words, expand differently when exposed to same temperature change. The reason bimetallic strip is important is because it is used in a wide variety of instruments such as thermostats, electric heaters, circuit breakers, iron, and fire alarms, among others. From its very name, bimetallic, you should be able to guess that it is made up of two metals: metal 1, which in this case is copper, and metal 2, which in this case is iron. These metallic strips are glued, pressed, or welded together to create one strip, which we know as bimetallic strip. The strip consists of different metal at the top and another one at the bottom. So when a bimetallic strip is heated, its temperature rises. Both metals start to expand, though by different amounts. In our case, let us assume copper expands more than iron. As copper expands more when heated, its change in length is greater than iron. This means that change in length of iron is less. As both metals are joined together and they expand differently, we see that the strip bends in a curve. Key point is that the metal which expands more, in this case copper, is on the outer edge of the strip because it has greater change in length. This is marked by the motion of the red dot, while metal which expands comparatively less, in this case iron, is on the inner edge of the strip because it has lesser change in length. This is marked by the motion of blue dot. So when heated, the bimetallic strip deforms in a curved direction. The metal on the outer edge has expanded more, while the metal on the inner edge has lower rate of thermal expansion. When a bimetallic strip is cooled, its temperature falls. Both metals start to contract, though by different amounts. In our case, let us assume copper contracts more than iron. As copper contracts more, when cooled, its change in length is greater than iron. This means that change in length of iron is less. As both metals are joined together and they contract differently, we see that the strip bends like a curve. This time, the direction is opposite to when it was heated. Key point is that the metal which contracts more, in this case copper, is on the inner edge of the strip because it has greater change in length. This is marked by motion of red dot, while metal which contracts comparatively less, in this case iron, is on the inner edge of the strip because it has lesser change in length. This is marked by motion of blue dot. So when cooled, the bimetallic strip deforms in a curved direction. The metal on the inner edge has contracted more, while the metal on the outer edge has lower rate of thermal expansion. The change in mechanical property of bimetallic strip as a response to temperature variation is useful in many different instruments. One such device is thermostat, which is used to regulate the temperature of a room to a specific range. The image shows a typical structure of a thermostat. We have the bimetallic strip made up of two metals, brass and invar, which is connected to the battery source. Then we have a steel spring positioned directly above the bimetallic strip. Both the steel spring and bimetallic strip have two metal contacts at one end. When joined, they allow current to flow through. Above the steel spring, we have the control knob, which is used to regulate the temperature. All these components are connected to electrical and heat-proof frame for support. In this circuit, the heating element is the main circuit to which the electric current flows. So we are dealing with an electric heater. Other elements of the circuit include wires, which connect the steel frame and bimetallic strip to the power source, and different connectors in the circuit. Soon the image will show how bimetallic strip works in a thermostat to regulate the temperature of an electric heater. When the control knob is pushed down, it makes contact with the steel spring. The force exerted pushes the steel spring further down until the contacts touch, allowing current to flow in the circuit. The current here is shown by the glowing red lines. As current flows, the heating element starts, and this steadily increases the temperature of bimetallic strip. Once the temperature has reached a certain limit, the bimetallic strip starts to bend away, breaking contact with the steel spring. This stops the current flowing in the circuit. As you can see that as the temperature drops, the bimetallic strip returns to its original position. At 36 degrees Celsius, the bimetallic strip contacts the steel spring and the current starts to flow again. Bimetallic strips are also used in fire alarms. The circuit is largely like a thermostat. We have a wooden board, fixed end, and a stand for support. The bimetallic strip is made up of invar and brass. It is connected to an electric bell and power source through wires. A movable screw allows bimetallic strip to make contact and complete the circuit. When a fire is placed close to the circuit, the temperature starts to rise. Bimetallic strip starts to bend until it contacts the movable screw. Once in contact, the current starts to flow in the circuit and the electric bell starts to ring. Just to summarize, bimetallic strip is made up of two metals joined together. In this case, one is brass and the other iron. The strip is flexible, meaning it can deform. When the strip is heated, both metals expand differently. As a result, it deforms into a curved shape. Metal that expands more is on the outer edge, which in this case is brass. Meanwhile, iron is on the inner edge. Now, when the strip is cooled by pouring cold water, it contracts back to its original shape. If cooled further, the metal contracts even further and the strip bends in the opposite direction. Thermal expansion of liquid is used in thermometers for temperature measurement. Liquid mercury absorbs heat energy and thermally expands. Its volume increases and it rises in the capillary tube. While the liquid absorbs heat and expands, but does the glass surrounding the mercury also expand? Yes, the glass also thermally expands, but the change in volume is so minute that it is considered negligible. This is also because thermal expansion in solids comparatively is much less when compared to liquids. This is primarily due to the presence of strong bonds holding the structure together in solids. Thermal expansion of gases is also very useful. Air surrounding the heat source expands and becomes less denser. As a result, it rises. This phenomenon is crucial in regulating the atmosphere of our Earth. Moreover, this is the reason hot air balloons rise from the ground. The festive lanterns you see are also able to float because of the heat source allowing it to soar through the sky.